Suara masuk. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, and good evening, depending on where you're from. Welcome to the Indonesian Philips Center of Excellence Regional Focus Group Discussion, June 2026, with the topic of satellite application for weather and environmental hazard monitoring. The honorable speakers, also all participants of this meeting. I'm Aferus, and I'll be the moderator of today's agenda. I'm very pleased to see you here and welcome you to this meeting. Before we begin, I would like to introduce you to all the speakers. The first is Bodo Ziski from BOM Australia, who will give the materials by video recording about using geostationary satellite data for hotspot analysis, including forest fire detection and monitoring. And the second is Nadine Ayasha from Haji Hasan Meteorological Station, Kota Waringin Timur, PMKG Indonesia, who will presenting about utilization of Himawari 9 satellite RGB techniques for extreme weather analysis. Now, let's continue to the main session, the presentation from the speakers, and continues to the Q&A session. Let's start with the first presentation by Bodo Ziski from the BOM Australia. To the TSO, please share the video.
Hello, I'm Bodo Zeshki. I'm a teacher at the Australian Bureau of Meteorology Training Centre. I'm also the point of contact of the Australian VLab Centre of Excellence. I've been invited to present at today's Indonesian VLab Centre of Excellence Regional Focus Group meeting. I'm sorry that I cannot be with you today as I'm currently on leave. However, my colleagues from the Indonesian VLab Centre of Excellence, Ms. Ani Arumsari and Mr. Kafid Rizki Pratama of BMKG Indonesia, have kindly agreed for me to prepare this recording. Please forward any questions you may have to the coordinators of the Regional Focus Group meeting, maybe via the chat box, and I will attend to these once I return from leave on the 1st of July. The topic of my presentation today is using geostationary satellite data for hotspot analysis, including forest fire detection and monitoring. I thought it would be a good idea to reference resources from the Australian VLab Centre of Excellence Regional Focus Group meeting archive, because this is a resource that I hope you will find really useful. Here are the contents of the presentation. First, I will look at the early warning for all priority hazards fire weather regional focus group meeting recordings on the Australian VLab Centre of Excellence webpage. Secondly, we'll look at the satellite bands and RGB composites relevant to fire detection and monitoring. Then, we will look at how utilizing geostationary satellite rapid scan imagery can be used to assist in fire detection and monitoring with an example. I will look at some case studies from previous regional focus group meetings, highlighting the satellite monitoring of fires, including forest fires. Finally, we're going to compare satellite versus aircraft monitoring of hotspots, also polar versus geostationary satellite images monitoring hotspots, and we'll look ahead to the potential of Himawari 10's capabilities. Right, let's start by looking at the Priority Hazards Fire Weather Regional Focus Group meeting recordings on the Australian VLab Centre Excellence webpage. On this slide, I've shown the new location of the Australian VLab Centre of Excellence resources including the archive of the regional focus group meetings. Here are the steps you would take in order to access these resources. This slide is a summary of the specific presentations that deal with fire weather. As you can see, these cover examples from a number of locations within the Australasia Pacific region. Next, let's look at the satellite bands and RGB composites relevant to fire detection and monitoring. This slide is a nice summary of the important satellite bands that are used for fire activity detection and monitoring. It shows a fire, the associated smoke and pyrocumulus cloud, and also the land cover surrounding the fire. This is rendered in the MODIS 721 RGB composites. Note, firstly, that the 2.3 and 3.7 micron bands are the principal bands used for hotspot or fire detection. These bands also permit fires to be detected through smoke. For the smoke itself, the 0.47 micron visible band in the blue part of the spectrum is useful. That's because smoke scatters more radiation at short wavelength. On the other hand, the striking contrast of a brown smoke plume against the white clouds and the darker surface of the Earth, as rendered within the true color RGB composite, makes this very useful for smoke monitoring. Pyrocumulus cloud, as may be generated within the smoke plume, is well detected by the visible bands and also by the 0.86 micron band. When monitoring fire development, it's also important to consider the land cover, as this provides the fuel for the fire. For the examination of the land cover vegetation, it is very reflective in the 0.86 micron band. Even the smallest hint of vegetation will result in a strongly reflected signal in this channel. For the identification of burn scars, soil is reflected in all bands, though a little bit more in the 2.3 micron channel, giving it a reddish appearance in this MODIS 721 RGB product. Identification of burn scars are useful because these can retard subsequent fire propagation if the fire propagates into such regions. These regions can also be areas of enhanced erosion with deterioration of water in adjacent catchments. Here are some other RGB composites that can be used to detect and monitor fire activity during the daytime. These include the Day Microphysics RGB, the BMKG Smoke RGB, the Fire Temperature RGB, two versions of the True Color RGB, one with the Rayleigh scattering removed from each component band to sharpen the image. And, of course, the MODIS 721 product discussed previously. Right, let's check out what the RGB composites show. For this case study of the Wollemi National Park Putty State Forest Fire, the fire hotspots are rendered well in the Fire Temperature RGB, in the MODIS 721 RGB, in the BMKG Smoke RGB, and in the Day Microphysics RGB. The Fire Temperature RGB is also able to render the relative temperature of the fire source, with the hottest fires appearing white or yellow and the least hot fires appearing red in this RGB during the daytime. Smoke is best rendered in the True Color RGB composites. especially the version that has the Rayleigh scattering removed. Smoke is also rendered in the BMKG Smoke RGB and the MODIS 721 RGB. Smoke is poorly resolved in the day microphysics RGB and the fire temperature RGB. Finally, here are the recipes for the BMKG Smoke RGB, the fire temperature RGB, and the MODIS 721 RGB product. During the Australian VLab Centre of Excellence Regional Focus Group meeting of December 2023, Dr. Jordan Girth of NOAA NWS presented a case study from the Excellent Sims Satellite blog webpage. This case study investigated the use of satellite data to describe a fire-prone environment, focusing on Hawaii. A number of composites were shown, including the day land cloud fire RGB shown on this slide. Examination of the recipe of this RGB shows that it is a variation of the MODIS 721 RGB with different gamma enhancements applied here. During the Australian VLab Centre of Excellence Regional Focus Group meeting of March 2019, a case study of Australian fires from Victoria in Australia was presented. This included the application of the night microphysics RGB and the fire temperature RGB that are particularly useful during the nighttime. Here we show the animation of the 2.5-minute rapid scan night microphysics RGB as this transitions to the true color RGB during sunrise time. That's on the left-hand side. Note how the night microphysics RGB can clearly resolve the hotspots, whereas the true color RGB shows instead the smoke plumes at that location. Note the higher spatial resolution of the fire temperature RGB as rendered in the 10-minute data on the right-hand side compared to that of the night microphysics RGB of the same time. Finally, here are some useful online resources showing near real-time satellite imagery relevant to fire weather detection and monitoring. I've highlighted a fire and associated smoke over northern Australia from the 13th of June 2026. Firstly, here is the Sierra Slider Viewer from the Colorado State University and NOAA. Then, here is the SSEC Real Earth View from the University of Wisconsin-Madison. I would be very interested if colleagues can recommend additional near real-time geostationary satellite data useful for fire detection and monitoring as rendered on a web page. I would be happy to explore these resources and to develop future VLab case studies. Let's go on to looking at the using geostationary satellite rapid scan imagery to assist in fire detection and monitoring. Note that the Japan Meteorological Agency offers the Himawari Request Service. The Korean Meteorological Administration offers the request-driven GeoCompSat Rapid Scan Service, and the China Meteorological Administration offers the emergency support mechanism of Fengyong satellite. Here are some Australian VLab Centre of Excellence Regional Focus Group meeting case studies that include rapid scan monitoring of Australian forest fires. One from Queensland on the left-hand side, and the other from Victoria on the right-hand side. For this discussion, we will focus upon the Victorian case study as presented during the Regional Focus Group meeting of March 2019. Here are two true color RGB animations of the Bunyip fires to the east of Melbourne, Australia. The left-hand side animation is rendered in the rapid scan mode at 2.5 minute intervals. The right-hand side animation is rendered in the normal 10-minute image mode. Animation speeds are adjusted so that each animation takes the same time. Both animations are rendered in the rocking mode, that is, the animation goes forward in time and then backward in time. Note how much more detail is revealed in the 2.5 minute animation on the left-hand side. Let's study that a little closer. Here are some snapshots looking at various stages in the development of the fire as shown in the previous animations. That's from 03 UTC through to 0730 UTC. And let's explain this. First of all, the 2.5 minute imagery is better at capturing the life cycle of short-lived events. For example, the vigorous bubbling up of the smoke and the pyrocumulus. The better rendering of the rotation of the smoke. Revealing short-lived events in detail. For example, the episode of fire flare-up and injection of smoke to the higher levels. Finally, you can check out some near real-time rapid scan data on the Sierra Slider webpage. This renders both the Himawari 9 rapid scan and the GeoCompSat 2A rapid scan data in near real time. Here are some slides that are presented during the AMSUC 15 training event held during October of last year. You can follow the instructions on the slides and check this out yourself. This is for Himawari 9, and this is for the GeoCompSat 2A rapid scan data. Let's look in more detail about how satellite imagery can be useful in monitoring the detection and evolution of fires and associated smoke and pyrocumulus. We will also compare the satellite data against other observations. So we're going to look at some case studies briefly now. Firstly, we return to the Bunyip fire in Victoria as discussed previously. These satellite images were taken the day prior to the rapid scan example given previously. Here you can see the genesis of the fire. The true color RGB image taken at 01 UTC on the 1st of March shows no smoke over the area of interest. Later, daytime convective cloud developed over this area with associated lightning. You can see these in these red and orange dots. With the event of nighttime on that same day, the night microphysics RGB showed the first hotspots created by the lightning. Note that the detection of fire created by lightning from satellite would be much more difficult if the cloud persisted after the lightning activity had eased. Here is the same Bunyip fire again, this time just after the vigorous episode of smoke and pyrocumulus development and the associated injection of smoke to higher levels that you saw in the rapid scan imagery. This time, we're comparing the satellite image with a sounding taken at a similar time from Melbourne Airport, which is just to the west of the location of the fire. You can see the vigorous bubbling up of the smoke and pyrocumulus in the satellite image. You'll also notice the well-mixed layer in the low levels with the convective inhibition. You then note that the strong injection of smoke to higher levels is moving into an area that is less stable with southerly winds above 500 hectopascals. You can see here. So using the sounding in combination with satellite gives a lot more insight. Aside from the sounding, it's also useful to monitor the surface observations in the vicinity of the fire. Here we see the Lingkungan fire just to the east of the Bunyip fire in Victoria, Australia. This time, the image and observation data is from the 3rd of March, the day following the previous Bunyip fire example. This time, a cold front and associated cloud band is approaching the location from the west. Note the change in fire activity as we initially see the low-level northwest winds ahead of the front, and then as the front approaches, and eventually as we go into the development of a deep, well-mixed layer, into the moistening of the mid-level, and then with the low-level northwest winds turning to a more westerly wind direction. Mixing, the downward mixing of the stronger winds aloft, the enhanced mixing can also enhance the development of the fire's convective column, intensifying the fire behavior. Let's revisit the Hawaiian case study presented by Dr. Jordan Girth of NOAA NWS during the Australian Vlab Centre of Excellence Regional Focus Group meeting of December 2023. Jordan presented additional useful data that was referenced during the monitoring of this fire. And now we're going to look a little more at the polar orbiter data. So, a sequence of SUMI NPP VIIRS day-night band images from before and during the Maui wildfires, Maui being one of the islands in the Hawaiian island chain, is shown on the left-hand side. And this is being viewed using the SSCC Real Earth viewer. On the right-hand side is shown the synthetic aperture radar swath as the polar orbiting Sentinel-1A overflew the western Hawaiian islands at 0440 UTC on the 9th of August. Widespread 30-knot winds are rendered in yellow, and red, excess of 30 knots, are indicated. This clearly shows the strong winds that are funneled and enhanced by the Hawaiian Islands and that are related to the enhancement of the fires. Of course, this is polar orbiter data, and so this is not as frequent as the geostationary satellite data. But this data can be used to complement the information obtained from geosatellites for more effective monitoring of fires. Finally, let's compare the aircraft and satellite monitoring of hotspots and fire fronts. We will also compare between geostationary and polar orbiter data later on in this part of the presentation. This slide shows the development of the Bunyip fire in Victoria that we looked at earlier, as viewed by aircraft, this time outfitted with infrared line sensors, infrared line scanners. The images were forwarded to me by Mike Wilmot, a volunteer firefighter and a former satellite meteorology teacher at BNTC. The active fire fronts are revealed to a very high spatial resolution, and comparison across the images clearly shows the evolution of the active fire. Let's compare the fire as revealed in the Himawari fire temperature RGB with the image from the aircraft-based infrared line scanner over the Bunyip fire at around 0920 UTC on the 2nd of March 2019. Clearly, the aircraft data is of much higher spatial resolution, but in both data, it's possible to see the V configuration of the fire front. Finally, let's look ahead to how fire front monitoring may improve when the international community has access to the Himawari 10 data. This slide shows Himawari 10 and the spectral band characteristics of the 18 bands that will be available on the geostationary Himawari imager carried on that satellite. Notice that the important band for fire hotspot monitoring, the centered at around 3.8 micron, has improved spatial resolution for Himawari 10. This is at 1 kilometer sub-satellite resolution, whereas the current Himawari 9 3.8 micron band has a sub-satellite resolution of 2 kilometers. How might that improve fire front monitoring? Let's check it out. Recently, I referenced this Big Data Earth webpage showing a direct comparison between polar orbiter and geostation orbiting satellite imagery over the fires from the 2019 to 2020 Australian bushfire season. The higher resolution images are from the Sentinel-2 polar orbiter satellite, whereas the lower resolution pixelated image overlay is that rendered by Himawari 8. Here's the web page. So let's have a look at the animations that the Big Data Earth web page presents. Here we can see individual fire sources as picked up by the Sentinel polar orbiting satellite, and then superimposed on that is the pixelated data from the lower resolution data, hotspot data from Himawari 8. As we go down, you can see other examples where fire fronts are now displayed both in the Sentinel imagery and overlaid by the Himawari 8 data. Note that Himawari 10 will have a quarter of the pixel area. So each of these pixels you can cut out up into 4 parts, and that will be the resolution of Himawari 10. Because the sub-satellite spatial resolution of Himawari 10 is 1 kilometer, whereas the resolution of this data is 2 kilometers sub-satellites. I think the image comparison on this webpage is an interesting way to gain an insight into the potential of Himawari 10 in resolving fire hotspots and fire fronts in the future. That's certainly something to look forward to. Now I would like to summarize my presentation. During this session, I provided information about the fire weather RGB recordings on the Australian Vlab Centre of Excellence webpage. I introduced the satellite bands and RGB composites relevant to fire detection and monitoring, including the resources on the Cirrus Slider and the SSCC Real Earth viewers. I showed how geostationary satellite rapid scan imagery can be used to assist the fire detection and monitoring, also showing you some near real-time renderings of rapid scan imagery that you might want to explore. I presented some case studies from previous regional focus group meetings highlighting the satellite monitoring of fires, and compared the satellite versus aircraft monitoring of hotspots with reference to Himawari 10 capabilities. That is the increased resolution of the shortwave infrared band at 3.8 microns.
Okay, thank you for our GSO. And yeah, as Buddha said in the video, that any one of you that is have any questions for Bodo, please kindly write down the question on the chat box. And so the committee will collect it and send it to Bodo by email. So please, if you have questions for the materials for Bodo, write your question on the chat box and we'll send it to Bodo. And the answer will send back to you in 1st of July, like a Bodo, because he's out right now. Okay, and so now we'll continue to our second speaker, Nadine Ayesha. Is Miss Nadine Ayesha already here?
Yes, good afternoon.
Okay, good afternoon, Miss Nadine Ayesha. So we can continue. Are you all ready?
Yeah, I'm ready.
Yeah, okay. So
Okay.
to Miss Nadine Ayesha, the time is yours.
So, may I share my presentation slide here?
Yep,
Okay.
you can.
Oh, the sharing is not turned on, so I
Oh,
think
wait.
I have to request sharing.
Okay, okay. Just try again to share.
All right. Okay. Okay, good afternoon, ladies and gentlemen. First of all, let me introduce myself. My name is Nadine Ayasha. I'm from meteorological station of East Kota Waringin, but currently I'm on study leave at the University of Auckland, New Zealand. And today I want to presenting my presentation today about the utilization of Himawari 9 satellite RGB techniques for extreme weather analysis. So we are moving forward to the outline. Here I have 5 outline. First is Himawari 9 satellite introductions, and then RGB technique, and then the RGB method utilization, extreme weather analysis example, and then conclusion. Okay, let's talk about Himawari 9 satellite introduction. So meteorological satellites are Earth observing satellites equipped with sensors that continuously monitor atmospheric and surface conditions to support weather observation, forecasting, climate monitoring, and disaster risk reduction based on Giri et al. 2025. And then the Himawari 9 satellite is a Japanese geostationary meteorological satellite that has 16 channels with beta radiometric, spectral, and spatial resolution optical sensors than the previous generation of Himawari satellites, according to Beso et al. 2016. So particularly, Himawari 8 and Himawari 9 is basically just the same thing. They have the same function, they have the same channels, they have the same RGB method, but particularly now, Himawari 8 is just used as a backup of Himawari 9 satellite data. So if anything happened with Himawari 9, JMA still have the backup. So I'm pretty sure that this material is very famous actually since I was in my bachelor degree. We have a lot of technique and method for extreme weather analysis, right? Nowadays we have satellite data, weather radar, numeric weather prediction. We can choose whatever we want to make a comprehensive extreme weather analysis. But as I know, Himawari 9 satellite data has a lot of channels, right? Here we can see that there is a 16 bands of Himawari 9 satellite data. We have 16 channels. So my question now is, why don't we utilize the combination of some channels to create more comprehensive extreme weather analysis. So our extreme weather analysis is more comprehensive than usual. By combining some channels, I'm sure that it will advance your analysis than just using a single channel actually. Okay, here is the RGB technique. So first of all, I want to discuss about what is RGB technique or method actually. So RGB technique is used to improve the interpretation of Himawari night images by combining several spectral channels into red, green, and blue components so that the characteristic of clouds, air masses, and extreme weather phenomena can be identified more clearly than using a single channel, like I said previously, that uh, using single channel is good, but it will be more advanced if we combine many channels. So actually, RGB techniques has a lot of product. For example, like day natural convective, if I'm not mistaken. And today I just want to discuss about three products. First is day convective storm product. So what is day convective storm? So the convective storm is first to monitor convection processes and used during severe weather, and to identify cumulonimbus clouds with strong updraft, and also to distinguish convective clouds from other types of clouds. However, this product cannot be used at night, so it's only used at the daytime. And the composition itself is comprised of channel 3, channel 5, channel 7, channel 8, 10, and 13. So it has 6 channels to combine. Here is the explanation about the convective storm. So we can see here, this is the example of interpretation of the convective storm product in extreme weather event, actually. So we can see here in the yellowish color here, it means that there is a cumulonimbus clouds with strong updraft or high-level cloud with small ice particle. So if the interpretation or your picture resulted yellowish color just like this, it means that CB cloud exists when the extreme weather occur, and it can be the causes of the extreme weather itself. And this is the RGB receipt. Okay. We are moving forward to night microphysics product. So night microphysics is used to analyze cloud microphysics, latent heat released from water vapor into condensation nuclei and water droplet, and also to distinguish cumulonimbus clouds from other clouds at night, to distinguish low clouds from other clouds. However, this product can only be used at night. So if extreme weather happen in the nighttime, you can consider this product into your extreme weather analysis. The composition is just utilize 3 channels. It's only channel 7, channel 13, and channel 15. Here is the interpretation of the color from night microphysics product. First, if the picture of the image or the image shows the red color here, or this is a red brown color with the yellow dot, just like this. It means that there is a very cold cloud lower than -50 degrees Celsius with the high level cloud here. It means that cumulonimbus exists at that time that makes extreme weather more severe. And this is the composition of red, green, and blue. For the red color, we have channel 15 and 13 combining together. And then for the green color, we have channel 13 and channel 7. And then for blue color, they only use channel 13. So they have, each of them have their own function. All right, here is the air mass product. So air mass is used to analyzing air mass content and can be used for day and night. So it can add your report of extreme weather analysis to be more complete than before. So here is the composition. We have channel 8, channel 10, channel 12, and channel 13. So here is the interpretation of air mass product. If the picture of the satellite RGB shows a white color, it means that there is a thick cloud with the high level clouds. It means that there is a lot of air mass content in the atmosphere. So it can be the trigger of extreme weather occurrence at that time. And here is the combination of the channels in red, green, and blue. We can see here for the red color, there is a combination of channel 10 and channel 8. For the green color, there is a combination of channel 13 and channel 12. And then for the blue color, it's only use channel 8. Okay. Okay, let's talk about RGB method utilization. So I'm pretty sure that all of you have familiar with this. This is Satelit, the application that used to processing all of the channels of Himawari 9 satellite data. First, the preparation before data processing. Yeah, you have to download the Satelit GMSLPD software first, and then you have to download Himawari 9 satellite data in .z format. I'm pretty sure that all of you have that access from BMKG to download the satellite data. And then you just enter the Himawari 9 satellite data into Satellite GMSLPD. This is just a gentle reminder for you. So first, you just click the register menu here, and then when it appears, you just click files, and then you select the satellite files or channels to be processed. Okay, so this is manual guidance. There is automatic guidance, but also manual guidance. But as a weather forecaster, I think it's okay for us to understand the manual data processing first. It's quite easy as long as you downloaded all of the channels that you need and required for every product. Okay, for day convective storm, we need 6 channels, if I'm not mistaken, right? And then how to apply RGB techniques manually in the Satellite application. First, you have to click the gray menu here that I pointed here. And then you click color menu here. And then when the emphasize settings menu appear, press Ctrl plus mix simultaneously. And then you just here, you just you adjust the RGB settings based on the color composition rules. So you just follow this step, okay? And this is the automatic RGB data processing. So it's easier than manual. As long as you have download the required channels, it will result it in the image that you want. First, to automatically apply RGB techniques in the satellite application, you have to click option menu in here. And then when the option menu appear in the screen, you just click the RGB image list here, and then you just choose the convective storm, click apply, and then the picture is appear in the screen, just like this. Okay. It's just also the same thing for night microphysics manual RGB data processing. So you just have to download the channels that you need, and then the application for the manual data processing is just be the same, just like this. The automatic RGB data processing for night microphysics is also just the same as the previous explanation. So we just have to click the option menu and then click RGB image list, click apply, and then the interpretation will come up to your screen just like this. It is also be the same for the air mass too. Okay, and then this is for the automatic RGB data processing. So it's just the same, just as a previous section. And what I want to emphasize in here is if you have download the complete channels that you need, it will be appear just like in the guidance book from the RGB techniques. Okay, so this is a case example of extreme weather analysis. This is a old example, but I think it's still, based on my consideration, it's still relate for us and relate to if I make this as an example for the convective storms product. So 8 years ago, hail event occurred in Depok, 20 March 2018. So I tried to utilize the convective storms from 8 UTC until 11 UTC. So you can see here, there is a cumulonimbus development, particularly from 9 UTC here, and then 9, 10 UTC here. There's a yellowish orange colors. It's not that yellowish, but near yellowish color. So I can say that this is a cumulonimbus clouds. And the development process of cumulonimbus cloud from the growth stage here from 8 UTC until the dissipation stage at 11 UTC shows that there is a cumulonimbus that influence in the study area. So we can also set that there is an indication of strong updraft process when this event happen. Okay, for infrared products and RGB products in weather analysis. So the infrared channels and Himawari 9 enhanced product are commonly used for weather analysis. They are used to determine cloud top temperatures during extreme weather events. However, as a meteorologist, we need to understand the causes of extreme weather better. One way to do so is to utilize RGB imagery. For example, why do cloud top temperature reach minus 80 degrees Celsius during extreme weather? This question can be answered by utilizing RGB imagery. We all know that extreme weather is happen because of cumulonimbus cloud. but we can explain more for that situation. For example, this is happened because of cumulonimbus cloud, but there is also an updraft that drive this cumulonimbus growth. Okay, and how can we know there is an updraft? By using the day convective storm product, for example. So we know that it will be more comprehensive. And this is the case example of heavy rain in Sampit, 16 October 2020, using night microphysics product. I analyze from 11 until 22 UTC. So the RGB image from the 11 until 22 UTC shows strong cloud microphysical processes during extreme weather event. You can see here, as we discussed it previously in the RGB techniques. If the interpretation here or the picture here shows that there is a red color with the yellow dot just like this. Can you see here? This is a yellow dot. Yeah, it means that there is a strong cloud microphysical processing, which is a cumulonimbus cloud that drive all of this occurrence in the study area. Now we are discussing about air mass product tool. The case example is also be the same, just like the previous slide. It's in Sampit. We can see here there is a high air mass content in Sampit during the extreme weather event. So it's from 11 until 22 UTC. We can see here at 12 UTC, at 13 UTC. There is a white color, a thick white color. It means that there is a lot of air mass contained in the atmosphere. Okay, so I want to talk about the use of infrared channels and RGB techniques in weather analysis. So, using the RGB method, we can analyze things more depth. For example, why cloud top temperature are so low during extreme weather and why rain clouds linger for so long during extreme weather. We can answer this by the analysis from the air mass. We can see here there is a lot of air mass content in the atmosphere in the study area at that time. So that's why the rain linger for so long during the extreme weather occurrence. Okay, we are finally arrived to the conclusion. So first, the conclusion is RGB techniques from multiple Himawari non-satellite channels can be combined to produce images for extreme weather analysis. And then secondly, extreme weather analysis can be done by interpreting RGB image results such as day convective storm, night microphysics, and air mass product. And then the last is RGB techniques can provide in-depth weather analysis, making our analysis more complete. Okay, I think that's all from me. Thank you very much for your attention.
Thank you so much, Nadine, for the materials. So to all the participants, if any of you have some question to the speaker, to Nadine, please kindly use the raise hand button, and so we can please you to speak, or maybe you can just write it in the chat box. Anyone have any question maybe? Or maybe you can add some information or maybe discussion in the agenda. Maybe some of you from another country, from maybe different season or maybe different atmosphere wanna say or give us additional information related to the material. Okay. Anybody have a question or maybe an additional information for us? Because this agenda is a discussion, so maybe if there is no question, you can just add some information related to the materials from Nadine. Okay, there is maybe two questions here. Okay, maybe Nadine, you can write, you can read on the chat box from Mr.
Okay.
Ahmad first. Yeah.
Dear Mr. Boulder and Mrs. Nadine, I would like to inquire about the methodology. Is the RTP method combined with RTP analysis? If so, does this allow the resulting product to be generated automatically or not automatically? Does this allow the resulting product to... So, thank you for the question, Mr. Ahmad. So, actually, this is a manual guidance of RGB techniques. It's not yet applied or combined with artificial intelligence yet, but I think it's a good idea if we can combine it with artificial intelligence. So it I think it will be more accurate and also will be comprehensive tool for us as a weather forecaster. I think that's my answer.
Okay. Thank you, Nadine. And this we have a question from Patro Traore because it's from France. I asked Mr. Hafid to translate it to English. Good, good evening. I would like to know about the high resolution channels. Maybe you can elaborate some about the high resolution channels from the Himawari satellite.
High resolution channels. I think all of them has the same resolution. It depends on you how how you want to utilize or combine some channels, I think. But maybe if you using the other application instead of Satelit, for example, like maybe MATLAB or Python to combine it, I think you will result it in a high resolution, because if we process it with Satelit, it is just a usual picture. We will just get the usual picture. Yeah.
Okay, thank you. So that's maybe the third question from Ferdi. Can you describe resolution of RGB and show us the categories of the resolution?
Can you describe resolution? I'm sorry. What resolution that you mean? Because
Maybe Mr. Ferdi wanna speak on the Zoom, or can you elaborate the question, Mr. Ferdi? I'm sorry, Mr. Ferdi, your mic is off.
Okay, thank you, Miss Nadine and Mr. Averius. I mean, categories we choose, but we saw that the high resolution can you find about the cloud, extreme cloud, maybe. Excuse me, mungkin bahasa Indonesia ya, sedikit ya. Oke,
nggak apa-apa, Pak.
yang saya maksud bagaimana Mbak Nadine membuat resolusinya, kategorinya. Oh, ini yang ekstrimnya sekian, di bawah ekstrimnya sekian. Nah, itu mungkin kategorisinya apa itu? Atau dari warnanya kah atau apanya gitu? Mungkin itu yang saya maksud. Terima kasih.
Thank you, Pak, for the question. Okay, I will answer in Indonesian language. Jadi Pak, jadi saya membuat ini tuh berdasarkan manual guidance from JMA actually. Jadi memang step-step yang mereka jelaskan itu, misalnya kayak warna ini menunjukkan bahwa terjadi adanya extreme weather seperti itu atau pertumbuhan awan. Jadi memang menurut saya interpretasi dari RGB techniques itu memang a little bit more subjektif sebenarnya, kayak gitu. Dan kalau dari guidance-nya sendiri sih emang itu it's an old guidance, tapi memang subjektif kalau menurut saya karena lebih ditentukan oleh color, Pak, warnanya kayak gitu. Jadi it's depend to us as a weather forecaster to determine, untuk menentukan apakah warna ini menunjukkan terjadinya indikasi extreme weather, pertumbuhan awan, strong updraft, atau adanya massa udara yang banyak di atmosfer seperti itu.
Okay, thank you. So the
Terima kasih
categorization.
Mbak Nadine.
Ya, sama-sama, Pak.
Terima kasih, Pak Ferdi. Okay, so the categorization is depend by the colors, but also determined by subjective of the
Ya,
weather forecast. Okay. Okay, just 3 questions. Maybe any more questions from all the participants? Okay, I think there is no more question. So can we conclude this agenda? Okay, so thank you for all the speakers, Nadine, Ayasha, and all the participants from the participation here. Oh, wait, there's any more question maybe for Aloy Liu? Please use the microphone on the question.
Can you hear me? Hello?
Yes, clearly we can hear you.
All right. Miss Nandine,
Yeah.
my question is very simple. Your proposed methodology, is this a replicate from previous, let's just say, manual guidance for RGB, or is this your original idea? That's all.
Okay.
Thank you.
Okay. Thank you very much for the
Because,
question. This
because
is not.
principally this is forecast
Mhm.
based. Sorry for intruding.
Yeah.
That's
So
all. Yeah.
okay. So actually, this is not my this is from GMA guidance book actually, and I'm just citate it from them, and I just follow their guidance on how to combine every channels for the RGB technique. So not it's not my league to make the to make the product just like this. It's from GMA actually. I'm just following their guidance.
All right. Thank you so much, Miss Nandi. A
Yeah,
wonderful
you're welcome.
presentation. Thank you.
Yeah, you're welcome.
Okay, thank you for the just additional question. So we have reached our end of today's agenda, and maybe if any of you have more questions, just maybe email us or text us for the question so we can send it to the speakers, maybe for Nadine or for Bodo also. Thank you for your participation here, all the speakers and all the participants. I will say umpa-lumpa dan pedida. Let's wrap up to the agenda. Umpa-lumpa dan pedidi. See you in next RFG. Good morning, good afternoon, and good evening, everyone. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Pak Shishi.
Waalaikumsalam. Thank you, Faye. Thank you, Nadine.
Thank you. Terima
Thank
kasih.
you,
Gosip-gosip
everyone.
everyone.
Thank you,
Arigatou
everyone.
gozaimasu.
Terima kasih Mbak Nadine dan teman-teman semuanya.